Just okay, now let me make you the host. Yes, sir. The recording is on, and you are the host. You are. We are good to go. Thank you.
Thank you. Okay, hi participants for this free webinar by EDvantage Learning on petroleum geomechanics and carbon sequestration, challenges and solutions. So the term geomechanics looks very odd and huge, to be honest. So in the very beginning, when I was new to this domain of geomechanics, it is actually derived from soil mechanics of civil engineering and rock mechanics of mechanical engineering, and of course mining engineering. So we modified the name from soil mechanics and rock mechanics to geomechanics because we generally look at bodies that are in subsurface below the ground, right? So likewise, we have geology, geophysics, we have geomechanics. The main objective is to study the mechanical properties of rocks which have oil and gas in it. So we sometimes also call it as reservoir geomechanics, and of course, to make it common to to every domain in our industry, we call it petroleum geomechanics. And of course, there is a lot of relevance in carbon sequestration projects. So the very beginning slides will be very fundamental slides on stress strain and of course geomechanics, and then we'll dive into carbon sequestration and we'll see where geomechanics part comes in. So let's start. Uh, to give you a brief about stress and strain, because they are the building blocks of geomechanics. So we need to understand or analyze the stress and strain whenever we study rock mechanics. Since we deal with several geobodies like sandstones, carbonates, whatever, or igneous rocks and metamorphic rocks, right? So we need to understand the stability or the strength of rock. So on the right, you can see a body which is elongated, right? We are trying to apply tension on both sides. Yeah, force up and force down. So this force is acting on an area of cross section, right?
وانت موجود ما نرضى نتكلم يسكت وانت موجود.
Okay. So the body is now failed because it became into two different parts, right? So every body has a tensile strength or a limit of yield stress. Like before that, it will be intact. You know, it is a reversible process. So when we generally look at a body, when we plot stress and strain, right? A straight line comes which shows that body is elastic. And we presume that when we release stress, the body will come back to its original state. But one point comes where the body fails. So for a simple case of an axial loaded body, a cylindrical bar subjected to a tension or compression. Compression means we try to compress the body from both sides, right? So in tension, the length of the body will increase because the area of cross section will decrease. But in compression, the length of the body will decrease and area of cross section will increase. So if we apply force, namely stress or intensity of distribution of internal forces can be obtained by dividing the total tensile or compressive force F with area, cross-sectional area, right? So if you see on the second image, when you apply tensile force or tension, there is one normal force applying on the internal part of the body where the failure has took place. Okay. So normal force always acts on the direction parallel to the direction of force application. And you can see this force is now upon area will be the average stress that we apply on the block. So this can be obtained by dividing total tensile or compressive force of amplitude F by cross-sectional area A over which it is acting. In this case, the stress is a scalar because stress is not dependent on direction here. It's a scalar that represents an average stress over the area, right? So sigma average is F by A. So what we generally do is we try to uh, find the strain of the body. So strain in a sense, we try to see before failure, what is the change of length of the body with respect to original length. So we have linear strain, aerial strain, volumetric strain. In general, the stress is not uniformly distributed over a cross section of a material body, and consecutively, the stress at a point is different from the average stress over the entire area, right? Because we are trying to apply the force on the face of the body, but we don't know at the internal part, maybe somewhere here or somewhere here, what is the exact stress that's being acted. This is the force applied here.
Despacito, olvida tu cuerpo, las cosas al oído, para que te acuerdes si no.
Don't know what's happening.
Sir, kindly remove Rose, who is disturbing us.
Yeah, sure. Okay, let's see if it happens again. I'll remove. Okay, so the local stress at any point in the body, right, is defined as being the limiting value of delta F by delta A. So delta F is change in force to delta A change in area, and this delta A tends to 0 because I'm looking at a point, and the point won't have any area to measure. And yeah, and if the force is not applied perpendicular to the cross-sectional area, the stress can be decomposed into normal component called normal stress and a tangential component called shear stress. Because your application of force is trying to deform the body both axially and also aerially. So axially it is called by normal stress and aerially it is called shear stress, right? So if you look at any fluid, for example, let's look at a flow in pipeline. So I'll tell you where relevance comes of this. Yeah, remote. Okay. So if you see a pipeline where flow is happening, for example, okay. So we generally look at those velocity layers like this, right? The central velocity layer has more velocity, or the fluid layer, you can see. Okay. So your shear component of this turbulent flow that's happening will be on the layer between two slices of division. In the same manner, when I deform the body, maybe say by compression, right? So the body deforms in such a way that a shear failure plane will be appearing on the body, right? Where the sample actually fails, the body actually fails. So we take two stresses called normal stress and shear stress, right? And shear stress will be acting on the shear plane or failure plane. So when I was doing my research, my very fundamental research on geomechanics, so I am from actually sand control background. So I now work as a reservoir engineer, but my research was fully on sand control, that too through geomechanics in my master's and bachelor's. So that time I discovered that your compressional stress will generate shear strain on the block such that the body fails with a shear plane, right? So it all depends on the body's mechanical nature or physical nature, to be honest. So depending on those normal stresses, sigma x, y, z, and shear stresses tau x, y, tau x, z, y x, y, z, z x, z y, we form a stress tensor. So generally, any anisotropic parameter, maybe say permeability or whatever, so they have three components if it's a vector. But if it has 9 components, we call it as tensor. So to provide a complete description of stress state at a given point, we must be able to identify the stresses related to the surfaces in 3 orthogonal directions. So if I'm applying stress on, x direction or x plane, maybe say let's draw another body here, a cylindrical body. Applying stress, compressional stress from both sides on the area, right? With a force and of course area of cross section. So this stress application on x direction only on one axis might generate shear stress on two other directions, xy and xz. So you can see this normal stress and its corresponding shear stresses, tau xy and tau xz, where my application will be on x-axis, but my failure will be on y-axis or displacement or disarrangement, right? So there are 9 components of stress at any point given by the below tensor expression. And of course, we need to always recategorize them to limiting stress. Delta F by delta A, limiting delta A to 0, because I want to know at a point. Similarly, we have invariants which remain unchanged during a change of coordinate system. So we generally take mean stress as sigma x plus sigma y plus sigma z by 3, because we want to consider or calculate the deviatory stresses. The mean normal stress is equal to trace of the stress tensor matrix. What is trace? The average of diagonal elements, sigma x plus sigma y plus sigma z by 3 is the mean stress that is acting on the body. So next comes deviatoric stress. The objective is we want to define the average stress, right? The average stress defined previously expressed a uniform compression or extension, right? It's a uniform compression extension, and we want to find what is the equivalent or proportional shear stress. But distortions are expressed by deviatoric stress tensor. Distortions means if I am trying to look at my net stress, excluding mean stress on the x direction, my net stress excluding mean stress on the y direction, my net stress excluding mean stress on z direction, that is deviatoric stresses, which are given by x, sy, and sz. So they can be obtained by subtracting the mean normal stress components from the stress tensor. So now sigma became s, called deviatoric stresses. So you can see if I'm applying stress on one direction, sigma 1, and stress on other direction, sigma 2. So you can see on third plane there is a normal stress. So your sigma 1 will be going parallelly, right, from the other face. Sigma 2 perpendicular to the other face. But a normal stress will be acting on the point, and my current research will be on this point. I want to see what happens at this point as a limiting stress, right? And of course, your tau n. So for equivalent sigma normal stress, your tau n shear stress will be acting on the body, aerially. So in this manner, if I assume that there are no shear stresses, there are no shear forces acting on the body with the equivalent normal forces. So then comes principal stresses. At any point of a body, subjected to system of forces, there are 3 planes which can be defined on which there are only normal stresses and no shear stresses. So that is for a point. So these planes are called the principal stresses or principal planes, and the stresses are called principal stresses. So you can see tau xy, tau xz, tau ix, tau yz, and tau zx and tau yz are 0. So in this coordinate system, the stress tensor is a simple expression, and it is not anymore a tensor, it's a vector, because your application is on 3 directions. So now relating this to the actual scenario in oil and gas industry, we generally have 3 stresses in subsurface, which are sigma v, called vertical overburden stress, sigma h max, called max horizontal stress, and sigma h min, called min horizontal stress, right? So these 3 stresses are what we should understand, and they have direct relevance on carbon sequestration projects, because we are artificially increasing the pressure of the reservoir, be it aquifers or depleted oil and gas reservoirs. The 3 principal stresses are known as major, intermediate, and minor principal stresses. For a normal stress state of the body, we have sigma v peak, sigma h intermediate, and sigma h small min, right, in decreasing order of magnitude. Okay. So now, as I was talking about this experiment, our objective is just to see the failure plane, right? So what we do, we generally do an experiment called triaxial test. So triaxial cell is a cell that contains your axial loading frames from the top and confining stress given radially. So if you just understand this properly, let me just draw a bedding plane. For example, your surface of the ground and there's a bedding plane going like this, right? So in this bedding plane, you can see, assuming a cylindrical body or radial body, that is, that is what we can see. So you can see from the top and bottom, there are some forces acting on the body radially, right? From all directions. This confining pressure will be representing that radial force. And of course, your overburden stress due to fluid flow, whatever, will be sigma V on the body. So confining pressure is actually sigma H min. H min. And your axial load that we give is sigma V, right? So we artificially will try to give these two stresses on the conventional triaxial test. So in triaxial test, what we do, we try to confine the body with a radial fluid, with a radial pressure, of course, of 1 bar, 10 bar, 5 bar, whatever it is, right? And we try to give the load on this body from on the axial plane. And of course, our objective is to see the shear failure line of this body and up to what load this body is handling this load. So what we do, we'll try to plot your stress versus time. And we will see if we'll keep increasing stress. At one point of time, the body will fail and will release the stress significantly and or instantly. And this is actually force that we give in newtons or kilonewtons. And we convert this force to stress, which is force upon area, right? And general configuration of triaxial cell is that now triaxial cell, your confining pressure is given by a radial force, by a fluid, to give your radial stress artificially. That will directly mimic your subsurface happening. So there is a membrane between the sample and the confining system. Because the confining system, the confining pressure fluid won't be in contact with the sample. So generally in triaxial test, we have some ASTM standards, American Society for Testing of Materials, where we try to take L/D ratio of more than 2. If I have a sample of length, maybe say 1 meter, 1 meter is too high, maybe say 100 centimeter. My diameter should be less than 50 centimeter. So L/D is more than 2. So they are standards. And now the main thing is we need to also see the strain, because what Hooke's law states, for an equivalent amount of stress, there is an equivalent amount of strain also being generated until the body fails, until this point, right? So we can get strain from LVDTs. They are transducers where you have strain gauge affixed. So to see what is the equivalent strain of the body, I'm applying compression, right? So what happens, I have already told you, in compression, your length will decrease, but your area will increase, right? Area will increase. So you want to see what is the increase of area from these strain gauges affixed. So these are transducers, which will try to tell us what is the equivalent, reduction in length, delta L. So we will see what is the strain at this stress of failure stress at sigma failure. Okay. So this is the actual representation. Let me just erase. Right. Yeah. So you can see this is how we give the load on the triaxial sample, where you have jacket separating your radial fluid for confining pressure and your sample, and we have pore pressure acting with the load. So generally in triaxial test, we have two different tests. One is conventional, one is true. In conventional, as I've already told you, in subsurface, in geobodies, we have three stresses: sigma V, sigma H max, and sigma H min, right? So these three stresses can be artificially mimicked in triaxial setup. How? In TTT, true triaxial test. In true triaxial test, what we do, we try to give the load from bottom also, or load actually is given by the top upstream pore pressure. In this you can see upstream is here and downstream is here, right? We give load from both sides. So one load is sigma H max, or sorry, sigma V. Sigma H min is your radial stress, and sigma H max is your second axial, right? this actually honors the thing that's happening in subsurface due to fluid flow. But in conventional triaxial test, what we generally assume is that your sigma v is higher, but your sigma h max is exactly equal to sigma h min. H max is equal to sigma h min. The reason being, we are not giving the second axial stress from the bottom. We are only applying load from the top. That isn't conventional triaxial test. Okay. So when I was researching in my masters, I was doing this experiment only, conventional triaxial test.
Darling, just kiss me slow. Your heart is so.
Okay. So from this experiment, the main objective is to generate a Mohr circle. So Mohr circle is a very beautiful description of what's happening, you know, where your sample is failing and what should be your safe stress state or safe stress during injection of fluids like carbon dioxide in supercritical state. So what we do, we try to plot shear stress and axial stress on x and y axis, and we get a semicircle. So in semicircle, you can see sigma 1 is nothing but your vertical overburden stress or axial stress that you give. Sigma A is sigma 1. And sigma 2 will be your confining stress, PC. Right? So from sigma 1 and sigma 2, we already know sigma 2. We'll fix it with confining cell. And sigma 1 is what we get from the experiment of triaxial test. We draw a semicircle, and this semicircle will give the failure region. So if my stress is at any point in the semicircle, if your stress is at any point above the semicircle, your sample will fail. You know, that is not a good stress state for your current geobody configuration in subsurface. So we draw a semicircle with radius sigma 1 minus sigma 2 by 2 and center sigma 1 plus sigma 2 by 2, right? This 2 theta is an angle, and theta is actually called friction angle. Yeah, friction angle, you can say. If you draw a straight line here and draw tangent like this, right? Maybe something like this, tangent here. Yeah, draw a tangent here and take the horizontal plane. That theta is called friction angle. Okay. And you have some property called here called cohesion, internal cohesion. So let me just we'll draw a tangent like this to the Mohr circle. This is called cohesion. So our Mohr circle is based on Mohr Coulomb failure criterion. So tau is equal to tau naught plus sigma cos theta. Right? This is the equation. So this is the equation for this line. So tau naught is the cohesion, internal cohesion, and theta is the angle or friction angle, you can say, right? So it has more relevance on, you know, tunneling for mining. But yeah, Mohr circle is a very important representation of what's happening in the subsurface. At what stress my sample will fail. If I take a stress like this here of sigma 1, somewhere between sigma 1 to sigma 2, and of course your shear stress is more, sample will automatically fail. So our general convention is that if your sample, if your stress state is, you know, somewhere here above the Mohr circle, your sample will tend to fail. But if it is within the Mohr circle envelope, it won't fail. So that is what we want to see, depending on the injection of carbon dioxide with a very high pressure, because in sequestration projects, we always need to inject CO2 in supercritical state, and carbon dioxide has, I think, 7,500 psi critical pressure, right? So when we inject more than the 7,500 psi critical pressure, what happens? Your injection, maybe if we don't know the actual frac gradient of the formation, the fracture gradient, the formation will fail. And what happens? The CO2 will leak off. So for a safe and contained storage, we need to also understand the current stress state of the subsurface formation that we're targeting, and also the long-term storage efficiency. That's quite important. So in this regard, we will generate a 1D mechanical earth model. So 1D MEM is that important mechanical earth model, which we generally generate for any formation depending on the open hole log. So the input for 1D MEM is open hole log. The objective being we try to evaluate the properties, subsurface properties. like Young's modulus, shear modulus, and UCS, and of course Poisson's ratio. So we have several correlations to generate these all properties from open hole logs like gamma ray, density, neutron, and sonic. These four are the primary inputs for mechanical earth model for open hole log. And that open hole log, we have several correlations for different formations, and we can generate these general for mechanical properties, and also we generate shear bulk modulus also. Young's modulus, shear modulus, bulk modulus, UCS, and Poisson's ratio. And also we can generate tensile strength of the rock. So this will give us, the current signature of the formation. Maybe say you can see gamma ray is quite low here. It may be sand, clean sand, but actually the values are quite high. But yeah, there can be a good sand presence here, and you can see equivalent strength of the rock is decreasing here. Young's modulus decreased, shear modulus decreased, UCS decreased, and Poisson's ratio increased, right? So when you inject CO2 in the sandstone, in the sand bearing formation at a very high stress, more than the UCS, the formation will fail. So 1D MEM will try to give us that understanding of the current stress state of the formation, and we can understand, our safe injection pressures and of course rates from MEM. So the main fundamental of geomechanics is for a safe and contained storage, what should be our approach in selecting and designing a storage project. So now let's talk about geomechanical modeling, especially in CO2 sequestration. So we can see already we have discussed about this, that from static property model and dynamic reservoir model. From static model, for a subsurface reservoir, we get structure, faults with 3D seismic and 1D GMM or geomechanical model. GM is geomechanical model, or MEM, mechanical earth model. So why it is called 1D? It is one dimensional, only with depth axis. And dynamic model, we get pressure, temperature, porosity, and permeability. Of course, these both are static parameters, but yeah, for history matching, we keep changing with multipliers. And we get the mechanical and strength properties with by coupling static property and dynamic property reservoir models. That will give us a geomechanical grid. So in several simulators, maybe say Eclipse or CMG and even T-Navigator, we currently have advanced geomechanical modules, right? So what we do, we try to give the stress state of that particular geomechanical grid that we choose. From what? From rock mechanical studies. The same thing, triaxial test. We will try to give sigma 1, sigma 2, sigma 3, and that will proportionately give us for each injection rate or pressure what is the equivalent increase or decrease in sigma 1, sigma 2, sigma 3. So this geomechanical model will give us with dynamic simulator and geomechanics simulator, we will understand change in temperature, pressure and saturation, and of course change in porosity and permeability. This will give us the field scale results, and of course by coupling this with CO2 rock interaction on rock properties. For example, in mineral trapping, the main objective of mineral trapping is that we want CO2 to be captured or trapped by minerals of the formation, right? So during CO2 injection, a reservoir may develop plastic behavior. Plastic behavior is a permanent deformation where stress path is not reversible. And of course, the pre-existing faults may reactivate. So we also have a famous term called fault reactivation, right? So what happens across faults? There are, if the faults have, proportionately high throws. High throws means more lateral displacement. Let me draw a fault here, for example. You have a fault like this. Okay. So you can see this is a foot wall and hanging wall. If I draw a vertical axis and if I take this, so this is the throw. The equivalent displacement of the fault plane with vertical axis, and this is called heave. For example, if the throw of the fault is quite high, so there can be a stratigraphic discontinuity such that your CO2 may be injected here, might leak and react to the fault. That also can happen. So I'll show you a slide on Sleipnir project for CO2 storage in saline aquifer. It started, if I'm not wrong, in 1999 with a storage capacity or injection storage model of 1 metric ton per day is the injection rate, I think, per year. So in that, what happened is faults got reactivated and CO2 got migrated into another layers. So we will understand that also in the next slides. So the main objective is we need to carefully estimate the stress field for design and performance assessment of an industrial CO2 injection operation. And injection of CO2 into subsurface formation affects the incident stress field because of HF. So if we don't know the frac gradient and we design an injection pressure such that we want to keep the pressure above the critical pressure of CO2 to inject it in supercritical state, it may generate fractures. Also, it may part the formation with a shear stress. And also we can observe expansion of host rock, and also fault may slip or reactivate. So currently geophysicists are trying to evaluate fault slip prediction. So they are understanding or analyzing how the fault slips even more. So during deposition, the fault plane is like this with a uh, categorized or formed throw and heave. But with injection, your fault may further slip or throw may further increase, thus creating a fault pathway for CO2 to escape. So that is also to be understood. So during CO2 injection, to deplete hydrocarbon reservoir, the initial stress state would be recovered because the term depletion means the pressure is depleted and volume is also quite less. If there is a weak aquifer, of course, we also need to look at the support of pressure naturally with aquifer. So what happens is with depletion of pressure, your initial injection rates are sufficient enough. We may choose a certain injection rate with a certain injection pressure, but the initial stress state would be recovered as the pressure is brought back to initial value, provided that the stress path is reversible during CO2 injection. Like if we remove CO2 again, the pressure might further decrease, but further increase in reservoir pressure would generally result in increase of the deviatoric stresses, as well as general reduction in the effective minor stress, thus leading to an increasing risk or shear failure called shear parting in strike slip fault stress region. So strike slip means your arrangement of sigma V, sigma H max, sigma H min is different. So generally sigma H max is more than sigma V in strike slip fault regime, right? So if you can recall, if any one of you are in petrophysics or reservoir, we generally perforate, in sigma H min direction, and also we choose a mud weight such that it won't exceed sigma H min because we don't want formation to fracture. If you are trying to fracture the formation, we always need to maintain a stress more than sigma H max, right? So we always try to fracture the formation in a direction perpendicular to sigma H max. But yeah, with the further increase in reservoir pressure, there can be increased risk of shear failure in strike slip fault stress region. You can see an injection is going on, and this injection may lead to fault slip, and increase in pore pressure along fault requires high permeability pathway to let CO2 be stored. While estimating the storage capacity, we always take porosity into play, but we don't take permeability into play, right? That is also important. So injection induced pressure increase, if sufficiently large, could lead to compromise of caprock seal. So when we look at a certain CO2 storage site, we always also look at the caprock seal integrity, because that is what it further prevents CO2 to migrate. Maybe you can see here, generally we have advection as the primary chemical force or mechanical force happening in the reservoir, because when we inject CO2, CO2 will plume. CO2 plume will develop like a volume front such that this is a saline aquifer, right? So CO2 has generally less density than aquifer or water. So CO2 plume will be formed as a layer towards the cap rock. If the seal is not integral, then your CO2 may leak, right? The volume front is because of buoyancy and dissolution of CO2 and aquifer, right? So you can see how CO2 will escape. Maybe say if you're injecting CO2 here, and maybe a pathway is formed already with a weak cap rock, then CO2 may escape and it may go and be stored in the sea. That is what we don't want. We always want to look at these four storage options like unminable coal beds, depleted oil and gas reservoirs, saline aquifers, and salt caverns. But we also need to look at the potential leakage pathway like active fault, fracture zone, any abundant well, capillary pressure discontinuity, and diffusion losses due to injection. So these five also need to be studied. So injection induced pressure increase, if sufficiently large, could lead to a compromise of the caprock seal, and thus potential geomechanical consequences should be assessed prior to commencing CO2 injection. So what are the two main effects? Fracture dilatation due to increased pore pressure your fracture may get reactivated or fracture may form and fault may get reactivated, and also induce shear slip due either to raised pore pressures or reduction in normal stress due to buoyancy forces exerted by CO2 plume, of course. So sufficient representative and detailed characterization of potential storage site is important or essential for accurate simulation of long-term storage performance. So currently in across all countries, CO2 storage is restricted to simulation and research work only. Not many people are going ahead with storage projects because economics is a matter of concern, and also your long-term containment. It's also a matter of concern. So geomechanical characterization of the host and cap rocks of target reservoir and assessment of long-term behavior of overburden in a CO2 storage scenario requires determination of mechanical properties of these rocks. Of course, your 1D mechanical earth model is such a kind of model that will give us the mechanical properties of these rocks. Right? You can see here, right? I'm injecting CO2 below cap rock, assuming that it'll be stored for a longer period of time. But you can see fault is getting deactivated, and through fault it is migrating to other layers, and through fracture zone it is again going up. Right? Again, it is generating emissions. For geological storage of CO2, an important element of the model is whether conductive fractures exist within the cap rock. We always need to check that. So generally what happens is, currently several researchers are also suggesting that before you choose a site, always go with seismic, 4D seismic. So after a certain period of production, maybe 10-20 years, we should do seismic again to understand what is the current change in subsurface structure, to see whether there are any reactivated faults, because we always can't look at the initial interpreted seismic, because with production a lot of mechanical changes happen in the rock, in the formation. So it is advisable to go for seismic survey before starting up injection project. So site characterization is important, as we need to give particular attention to collecting data for primary cap rock and describing its properties relevant to storage containment. Containment is a matter of concern. Also, we always need to look at damage envelope for more Coulomb failure criteria and can give detailed insights. Right? We need to see, even though we need to inject CO2 in subcritical state, but will the formation has any negative effect based on more Coulomb failure criteria? We should always be between the damage envelope. We should not exceed the stresses above the damage envelope, right? So there's a project, Inshallah storage project in Algeria, in Krechpa field. So this took place between 2004 and 2011. So in this I think 7 years, the rate was 0.5 metric ton per well per year. The formation was deep saline aquifer, carboniferous sandstone, and depth was around 1.8 kilometers. So they're getting natural gas with 10% CO2, and they're separating CO2 with amine-based plant, and that is being injected in 3 horizontal wells. So the sandstone is very tight, of 1 milldarcy. Produce gas and inject CO2 in injection wells in the water or aquifer, right? So seal is thick shale with fractures and faults. So risks were cap rock integrity concerns. Your seal is thick shale, but it has faults and fractures, and they may get reactivated due to uplift and pressure anomalies. And also they have understood that potential fault reactivation may also take place. So they suspended the injection in 2011 to mitigate these risks. But yeah, with this much rate, they achieved good injection capacity. And the second project that I just wanted all of you to look at is Sleipner CO2 storage project. It started all the way in 1999, right? This link can be browsed by you. So in this, if I'm not wrong, they are injecting 1 metric ton per year across, I think, 3 wells. I'm not really sure, but yeah, you can just go and look at this paper. I'll share this paper with the EDvantage team. They will share it with you. Just look at the paper. It is similarly to Inshallah project, but yeah, it's a very good project. And of course, this project supports that we need to always go for 4D seismic. So to summarize, what are the subsurface risks in geological storage? So CO2 gas pressure exceeds capillary pressure and may pass through siltstone, which is the cap rock, like shale, right? So since we are injecting CO2 in such a way that buoyantly it will migrate up and form a plume. And of course, free CO2 leaks from A into upper aquifer fault, maybe from A into upper aquifer fault. Sorry, upper aquifer upfault through the upfault. and CO2 can escape through gap in cap rock into shallow aquifer, because cap rock is might generally be not an integral, even though it has zero permeability. It may we may create artificial fractures, and that may lead to leakage. Also, in D, injected CO2 migrates up dip, right? It has less density and increases reservoir pressure and permeability of the fault. And in E, you can see CO2 escapes via poorly plugged old and old abandoned oil well. So in abandoned wells, what we do? We plug the well with cement plug or bridge plug, and we abandon the well if it is dry. So of course, with increasing pressures in the reservoir, this plug may uh, this plug may get suspended or spoiled, and your CO2 may again escape through the abandoned well. That is also a matter of concern. Also, natural flow dissolves CO2. Your F, natural flow dissolves CO2 at the CO2 water interface and transports it out to closure. And if you see, this is G, CO2 escapes to atmosphere or ocean. And of course, you're injecting CO2 through this injection well, and it is being escaped because there is connection, or it is connected. There is no structural discontinuity, right? So these 7 can be subsurface risks that we always need to look at. So cap rock integrity failure, where CO2 can migrate through faults, fractures, or poorly sealed wells, the cap rock is compromised. Also, wellbore leakage, CO2 may escape through existing or abandoned wells. Induced seismicity, this injection pressure increases pore pressure, potentially reactivating faults and causing earthquakes. Also, unintended migration of CO2 or brine. CO2 or saline water may migrate outside the intended storage zone because the water is being contaminated with CO2, may migrate. Also, geochemical reactions between CO2, brine, and minerals can alter the formation properties. So, if you look at the 4D seismic, the main objective of 4D seismic is the fourth variable is time, right? So, with time, we can see how the formation is being varied structurally. We can see the formation properties, right? So, 4D seismic studies, which can involve comparing 3D seismic surveys taken at different times, are a valuable tool for monitoring storage and containment in subsurface formations. So, we can go for baseline and time lapse surveys where we do baseline before injection, and then we do subsequent 3D seismic surveys at various intervals. And also, we can determine CO2 plume, migration, and buoyancy. By analyzing changes in seismic reflections, the location and shape of plume can be mapped over time, right? Where the objective is to predict the free CO2 saturation. And also, we can assess the reservoir pressure and potential leakage, where the changes in reservoir pressure due to CO2 injection can be detected using photoseismic. Of course, the presence of localized pressure buildups or leakage pathways can be identified by monitoring seismic reflections. So that is all about our presentation. This is one more slide on mechanical earth models, where 1D and 3D mechanical earth models are crucial for assessing the geomechanical risks, because we need to determine safe storage capacity, prevent cap rock failure, and assess potential fault reactivation. So 1D is a very simple mechanical earth model where we plot every property with depth, with in situ vertical and horizontal stresses around the wellbore during and after injection. And of course, 3D MEMs incorporate 1D results with other models like seismic data to simulate the impact of CO2 injection on stress distribution and deformation within the reservoir and surrounding rock to help identify the potential risks and inform engineering decisions. Because if you look at Inshallah project, they have stopped injection in 2011 because to mitigate risks, because they have understood that cap rock integrity concerns are a matter of concern, like uplift and pressure anomaly. But if you have good photoseismic done, it is very important. And your geomechanical studies generally have this flow chart where we calibrate first lab measurement and viral logs. So lab measurement from special core analysis, we try to get the mechanical properties of log, and that will help us give the 1D and 3D for rock elastic and strength properties to build a geomechanical grid, and give boundary conditions like my sigma 1 is my max stress. Above that, your injection will stop. So that will give us geomechanical simulation with one-way coupling of stress and strain modeling. If the model is validated, no, again build your another geomechanical grid. If yes, we can transfer that back to Petrel and analyze, because Petrel is like a post processor. and we calibrate this observed stress. From what? From triaxial stress, right? So that's all for this webinar. I hope you got some insights. So questions, anyone? Yeah. Audio is not heard. Yeah, anyone questions? Am I audible?
Yes, sir, you are audible.
Yes, yes, yes.
Hello.
Yes.
So, which company this CCS project was implementing?
In Sleipnir.
Okay. Oh no.
No,
So, which company is implementing this project in that area? Um,
so Sleipnir is a field in Norway.
okay.
So they have started injection in 1996, actually, 1999.
Okay. Okay.
So there's a very good paper on Sleipnir project. You can just refer that. I'll share the link. Okay.
Yeah. Okay. Sure. Thank you.
So as of now, the first commercial storage project is Sleipnir only.
Okay.
And also, I have heard that in uh, by Equinor, the Volvo oil field, lot of studies are going on
Yes.
to plan injection in that field also because it is depleted.
Okay.
Yeah.
Thank you.
Yes. Thank you. Yeah, Sujit will share the slides. Any more queries, anyone? So just let us know your interest in this training. If you want, we can plan a 5 day, 6 day training for better understanding and your learning also. So yeah, that's all for today. Thank you for joining this webinar. Have a great night.
Yeah. Thank you, Vinod sir. Thank you, one and all who have joined and stayed till the last. So, yeah, thank you.
Yeah, thank you.